Basic chemistry of nanomaterials. Nanomaterials, they are defined as a set of substances which at least one dimension is less than approximately 100 nanometers. So that means a nanometer is 1 millionth of a millimeter, approximately 1 lakh times smaller than the diameter of a human hair. So this is the minuteness of these nanoscale materials or nanomaterials. The significance of these nanomaterial is very high because they show distinctive optical, magnetic, electrical and other properties like mechanical properties. These unique properties of these nanomaterials, they have great applications in the field of electronics, medicine, environment, and some other recent fields like gold refining also. Uh, the two main reasons for the unique properties of these nanomaterials is the most important one is the increased relative surface area of these materials. Nanomaterials, they have much greater surface area to volume ratio than the conventional materials which we are having, and because of this greater surface to volume ratio, the chemical reactivity of these material becomes very high, and that is why they have a greater strength as compared to the conventional materials. And then new quantum effects, they lead to novel optical, electrical, or magnetic behavior of these types of nanomaterials. As far as history of these nanomaterials is concerned, it weighs back to 1857 when Michael Faraday synthesized the colloidal gold particles. However, the nanoparticles, they were converted into nanomaterials in late 1940s when fumed silica nanoparticles, they were manufactured by USA and Germany, and they were used as ultra-fine carbon black for rubber reinforcement compounds. Then nanoscale amorphous silica particles, they were used in many everyday consumer products ranging from non-dairy products to dairy products like coffee creamer to automobile tires, optical fibers, and they were also used as nanoparticles. They were also used as catalysts. Then in 1960 to 1970s, the very important development of magnetic recording tapes took place from the metallic nano powders that was reported. So this was the first instrument by which magnetic recording tapes they were developed. Then in 1976, nanocrystals, they were produced by inert gas evaporation technique, and recently Maya blue paint is a nano structured hybrid material which have been formed. So this is one of the painting which has been done by Maya blue paint, and this is a design for Maya blue paint. The classification of nanomaterials is that nanomaterials, they can be classified into these four types: uh, zero dimensional, one dimensional, two dimensional, or three-dimensional nanostructures. As far as zero-dimensional is concerned, the atomic clusters, filaments, and cluster assemblies, they cover under these zero-dimensional nanoparticles, nanomaterials. Then one-dimensional is the multi-layer nanomaterials. They come under one-dimensional, the nanofibers, nanowires, nanorods. All these they come under one-dimensional nanomaterials. Then two-dimensional nanomaterials, ultra-fine, grained, overlayers, and buried layers. All these they come under two-dimensional. The networks, the films, the plates, all these they are covered under two-dimensional nanomaterials. And then three-dimensional nanostructures, nanophase materials consisting of UQX nanometer sized grain. So these types of other all materials they come under three-dimensional nanomaterial networks. Then, according to size, the nanocrystals or nanoclusters, or which are defined as quantum dots, their diameter will range from 1 to 10 nanometers, and materials in which they are used, metals, semiconductors, magnetic materials. So quantum dots, they have this much of size. Then other nanoparticles, they range from 1 to 100 nanometers. All ceramic oxides, they may be converted into nanoparticles. Then in nanowires also, the size ranges from 1 to 100 nanometers, and nanowires can be made from metals, semiconductors, oxides, sulfides, nitrides. Then nanotubes, they can be formed from carbon, then from layered metal chalcogenides, they can also be converted into nanotubes. And then nanoporous solids, their diameter ranges from zero point 0.5 to 10 nanometers. The geolites and phosphates, etc., they are the examples of non-porous nanomaterial solids. Then two-dimensional array of nanoparticles, their diameter ranges from nanometer to millimeters, metals, semiconductors, and magnetic materials. Then surface and thin films, their thickness may be 1 to 1000 nanometers, and diversity of materials, they can be used as surface films or thin films coating with the nanomaterials. So this is a thin film coating in case of nanomaterials. Then these nanomaterials, they can be synthesized either by bottom up or by top down approach. So there are two methods, bottom up method or top down method, to synthesize various types of nanomaterials. So which means either we can assemble from small atoms into nanomaterials, or from we can disassemble from bigger particles to nanoparticles. So either top down or bottom up approach, both of these, they are successful in the synthesis of nanoparticles, and these nanoparticles, they can be transformed into different types of nanomaterials. Then these can be created based on methods of self-organization or self-assembly, which is sometimes called as biomimetic process. And using these methods, the synthesized materials, they can be arranged into useful shapes, so that the material finally can be applied for certain application. So depending upon the application, the method is chosen, that by which method we will get which type of nanomaterials. Then one most common method which is used for the synthesis of nanomaterial is biomechanical grinding. So mechanical abrasion or mechanical grinding is a top-down method for the synthesis of nanomaterials, where the material is synthesized by structural breakdown of coarser grained structures. And the advantages of this method is that this method is very simple, and we can make nanocrystalline materials with an very inexpensive equipment, and all kinds of materials they can be synthesized by this method. And then another advantage is that we can scale up to large quantities of materials for various applications very easily by this method. So these are the two main advantages of mechanical grinding. But the disadvantage is that there is a possibility of contamination when we will be doing mechanical grinding, and that means some impurities they will enter the nanomaterial. Then to consolidate the powder product without coursing the nanocrystalline microstructure is also a disadvantage. The mechanism of mechanical grinding is that this is usually done under high energy shaker, then planetary ball and tumbler mills. The energy is transferred to the powder from refractory or steel balls depending upon the rotational or vibrational speed, size and number of the balls. The ratio of the ball to powder mass, the timing of the milling and the milling atmosphere, that will determine that what kind of nano particles they will be produced by mechanical grinding. Then is wet chemical synthesis can also be used for the formation of nanomaterials, and here the two types of methods they can be used. The top down method here is that the single crystals they are etched in an aqueous solution for producing nanomaterials. For example, synthesis of porous silicon by electrochemical etching is a top-down method for the synthesis of nanomaterial. Similarly, bottom-up approach can also be used, and bottom-up approach is sol gel method or precipitation, which is done so that these materials they containing desired applications they can be formed. Now, these are chemical, physical, or biological synthetic methods to synthesize nanoparticles. In chemical synthesis, we will first dissolve the desired solution, then coating of those nanoparticles is done, and hereby we can synthesize different type of materials. Whereas in physical method, a laser ablation is done to synthesize metal plus solvent, metal nanoparticles in a solvent, and then those can be transformed into different types of nanomaterials. Then in biological synthesis, biological substances they are used for the formation of nanoparticle. So metal ions and biological substances they will be mixed to give us various types of biological nanomaterials. Then sol gel process involves the development of inorganic networks by formation of a colloidal suspension which undergoes gelation to form a network in a continuous liquid phase, which is a gel phase. So what happens is we will take a substrate, and through solvation this will be converted into sol formation, and this sol formation by spinning and dipping and calcine will be converted into thin film coatings for different application of nanomaterials. Or this soul formation directly by calcine can be converted into a nanomaterial powder. Then these soles which have been formed, they after dehydration can be converted into gel formation, and then supercritical extraction. Through supercritical extraction, it can be converted to aerogel, or through uh, addition of surfactant and thermal evaporation, they can be converted into zero gels, and then calcine can convert into ceramic nanomaterials. So this is how the through sol gel synthesis we can form different types of nanomaterials. So this is how the titanium dioxide is formed by sol gel method. Then properties of nanomaterials. The properties of nanomaterials are significantly different from those of atoms and bulk materials. And this is mainly because of the nanometer size of these materials. Because of that, the properties of these materials, they are very much different from the conventional materials. And because of these characteristics, the nanomaterials, they have very unique properties. They have large fraction of surface atoms, they have high surface energy, then there is a spatial confinement, and there are reduced imperfection. And because of all these four important characteristics, the nanomaterials, they have unique properties, and because of these unique properties, they find applications in many types of industry, like electronic industry, medical industry, environmental industry. All type of industries, they find applications for nanomaterials. Now, some of the important applications of nanomaterials, as I have told you, that they have wide range of applications because of their superior chemical, physical, and mechanical properties. And some of the important applications which are there for nanomaterials, they are used in fuel cells. They have been used in catalysis as catalysts. They have been used as phosphors for high definition television. Then they have been used in next generation computer chips. Then in environmental industry also, they have been used for elimination of pollutants. They have been used in manufacture of sunscreen lotion. They have been used as sensors in some cases. So depending upon the structure of that material, we can find out almost any application of these nanomaterials. They have been used in cosmetics also. They have been used as emitters in electronic industry. They have been used in nano devices. So there are so many applications in case of nanomaterial. Some of the more applications you can see from here. So they have been used as drug transporters. They have been used in cancer therapy. They have been used in tissue regeneration in the field of medical science. They have been used as biosensors. They have been used in bioimaging technology. They have been used in live imaging. Then they have been used in protein microassay. They have been used in cosmetics, nanomaterials. They have been used as fungicides. Then they have been used in amino acids, vaccines, gene therapy, therapeutics, and drug delivery. They have been used in. So these are some of the applications, very important applications of nanomaterials, and particularly these applications they are of nanotubes. Then different types of nanomaterials, they can be converted into fibers, membranes. They have been used in electronic industry. They have been used as thermal interfaces. They have been used in energy storage also. All these types of nanomaterials, they found different types of applications in different industries. Then carbon nanomaterials, out of different types of nanomaterials, carbon nanomaterials, they have very important role to play in case of engineered materials, and they include technical, medical, environmental and agriculture applications. And because they have been formed from copper, so they are environmental friendly also. The materials formed from carbon, they are organic materials, so they are environmental friendly also. So that is why they are very important also. During the relatively shorter time since the discovery of fullerenes, they are carbon nanomaterials, and they were discovered in 1985. Then in 1991, carbon nanotubes they were discovered, and in 2004, graphene was discovered. So, what are fullerenes, what are carbon nanotubes, and what are graphenes? We will discuss later on. But all these, they are carbon nanomaterials, and they have unique properties, these carbon based materials, and because of the unique properties, the different types of materials based on these graphene, fullerenes and nanotubes, they have been formed for large scale industrial production of these. So basically what happens is, we know that an allotropic form of carbon is graphite, and graphite can be changed into different types of other allotropic forms of carbon, which are carbon nanomaterial. We can form graphene, we can form carbon nanotubes, we can have fullerenes, then diamond. All these types of structures, they can be formed from graphite. So because of the unique properties, these are strongest materials, they have thermal and electrical conductivity, their electronic properties, they are very good. Then they have some electrochemical properties also, and because of these unique properties, they are strong, lightweight composites. They can be made from them, and then they can be used for thermal or electronic transport materials. They can be synthesized, and then next generation semiconductors, they can be synthesized from these. Then energy storage batteries, they can be formed from carbon nanomaterials. So they have vast number of applications, and as I have told you, the fullerenes, they are under zero dimensional nanomaterials, and carbon nanotubes, they are one dimensional metallic carbon nanotubes. Then graphenes, they come under two dimensional nanomaterials, and all others, they are this diamond and other, they are mostly three-dimensional carbon nanomaterials. So first is graphite. Graphite is one of the oldest and most widely used natural material, and we know that main ingredient of lead pencil is graphite, and industrial applications, they are carbon raising in steel making, battery electrodes and industrial grade lubricants. They all are made from graphite. Graphite has a unique combination of physical properties due to its macro molecular structure which consists of stacked layers of hexagonal array in sp2 hybridized carbon. So these sp2 hybridized carbon, they are united with each other in the form of hexagons, and they have a very strong covalent bond between the carbon atom in each layer. Then these layers, they are attracted to each other by weaker forces, so that these layers, they can be held together. And between the two layers, they are apart by 335 ppm, and the two carbons, they by 142 ppm. Then fullerenes, they are allotropic modification of carbon, and they are often termed as a molecular form of carbon or carbon molecules. This was, as I have told you, discovered in 1985 by Croto and Samble, and they were awarded Nobel Prize for their discovery in 1996. So the Fullerene family includes a number of atomic carbon cluster, and N should be more than 20, composed of carbon atoms on a spherical surfaces. And most common fullerene is C60. This is the most common fullerene. Here the 60 carbon atoms, they are joined by hexagons and pentagons in this fashion to form this fullerene. And here all the carbon atoms, they are sp2 hybridized and linked through covalent bonds. Similarly, if there are 70 carbons, then fullerene C70, 80 carbons, fullerene C80, all these types of fullerenes, they are they have been synthesized. The diameter of fullerene C60 is 0.7 nanometer. Then next is carbon nanotubes. Carbon nanotubes are one of the carbon allotropes with exceptional properties suitable for technical applications. And these carbon nanotubes, as I have told you, they were discovered in 1991 by Japanese researcher Azima. The carbon nanotubes, they are characterized by cylindrical structures with a diameter of several nanometers. So these types of tubes, they are known as carbon nanotubes. And these carbon nanotubes, they consist of rolled graphene sheets. So if we are having a sheet and we roll that sheet, that then roll a sheet of graphene, that will become a carbon nanotube. The carbon nanotubes may vary in length, diameter, chirality. Chirality means symmetry of the rolled graphene sheet, and number of layers. Based on the structure, they have been classified into two main groups: single-walled nanotubes and multi-walled nanotubes. If there is a single sheet of graphene that is rolled, then single-walled nanotubes, they are formed. If more than one graphene sheets, they are rolled into nanotubes, then we call those as multi-walled nanotubes. So this is there. If single graphene sheet is there, then single walled carbon nanotube. Two graphene sheets, they are rolled together, double walled carbon nanotube. Three graphene sheets are rolled together, then triple walled carbon nanotubes, they are formed. So this is also an example of triple walled carbon nanotube, because there are three different graphene sheet, 1, 2 and 3. So this is triple walled carbon nanotube structure, whereas here only one Graphene sheet has been rolled into nanotube. So this is a single walled carbon nanotube. Then is graphene. Graphene is a two-dimensional allotropic form of carbon formed by single layers of carbon atoms. And in graphene, carbon atom exhibit sp2 hybridization, and they are connected by sigma and pi bonds in a two-dimensional hexagonal crystal lattice. So this type of structure is there in case of graphene. So this is graphene, or this is graphene, and this is formed from graphite. So here the hexagonal crystal lattice where distance between the two carbons is 0.142 nanometers, and the first graphene sample was described in 2004 by Jim and Novoslav. He was a Russian British physicist, whereas Jim was Dutch British physicist. Both they discovered this special allotropic form of carbon which is called as graphene, and for their discovery they were given Nobel Prize in 2010. And similar to other nanomaterials, graphene, they also have unique physical properties such as extremely high mechanical rigidity and a high thermal stability. And because of this, these two unique uh, properties, they find applications in many fields. Then graphenes, as I have told you, they can be rolled into carbon nanotubes, and carbon nanotubes, they can generate fullerenes. They can be converted into fullerenes. Then is carbon nanowire. Carbon nanowire is a nanostructure with diameter of the order of nanometer, 10 power minus 9 meter. And it can also be defined as the nanomaterial where ratio of the length to width should be greater than 1000. If say length is 1000, then width should be 1 nanometer. So it should be greater than 1000. So length to width ratio should be greater than 1000. Then another definition of nanowires is they have been defined as structures that have a thickness or diameter constrained to 10 of nanometers or less, and an unconstrained length. Length should be high and thickness should be less than 10 nanometers. So this is another definition of carbon nanowires. And many different types of nanowires they exist, and they have been used for say superconducting. So that is these are called as superconducting nanowires. Then metallic nanowires, semiconducting nanowires, silicon nanowires, they are called as semiconducting nanowires. Then insulating nanowires, nanowires made of silicon dioxide or titanium dioxide, they are insulating nanowires. Then molecular nanowires, they are composed of repeating molecular units, either organic or inorganic. Organic, in case of organic, they are made of DNA, whereas this molybdenum mixture is from inorganic nanowires. Then these carbon nanowires, they find application in electronic devices, nanowire lasers, then sensing of proteins and chemicals using semiconductor nanowires. That has also been done by different types of nanowires. Then nanocones, carbon nanocones, they are conical structures which are made predominantly from carbon and which have at least one dimension of the order of 1 micrometer or smaller. So because that will make the cone if one dimension of the order of 1 micrometer or smaller is there. And the nano cones, they have height and base diameter of same order of magnitude, and this distinguishes them from tipped nanowires which are much longer than their diameter. So they are not as long as nanowires. Nanocones are smaller than nanowires in length. Then nanocones occur on the surface of natural graphite. The opening angle of the nanocones is fixed, and it may vary from 20 degree or 40 degree or 60 degree. So these three cones, they are preferred in nanocones. These have been used to cap ultra-fine gold needles, which have been widely used in scanning probe microscopy owing to their high chemical stability and electrical conductivity. So all these types of materials, they are called as nanocones. They have been reported, and some materials have been synthesized from nanocones. Then the lecture was mainly formed from material from this book, Chemistry for Engineer, which has been written by me, Harish Chopra, and Anupama Parmar. And some of the materials and images, they have been procured from internet sources. So internet has also been used for preparing this lecture. Thank you very much.